Hello, I'm going to do an addendum to video 8E, a very short video. It's going to explain a problem we had on page 150 of our lecture notes, but I'm going to look at it in a little bit more detail, maybe a little different way. This is the circuit right here. It has a 50 ohm source. It has a 50 volt source at 30 degrees that's driving an RLC circuit. The resistance is 25 ohms. The inductance is 20 millihenries and the capacitance is 50 microfarads. And I want you to look at that circuit just from a pure impedance standpoint like this. And I want you to tell me, what is the impedance looking into that circuit? I want you to think about that for a minute. Stop the video and think about it. And how would you answer that? What's the impedance looking into that circuit? Well, the answer is you don't know what the impedance looking into that circuit is because it's a combination of R, L, and C elements. It depends upon the frequency. We know that the inductive reactance is 2 pi FL. And we know that the capacitive reactance is equal to 1 over 2 pi FC. This is in ohms, this is in ohms. So this is the reactance, which is the imaginary part of that impedance. But notice it's frequency dependent. At certain frequencies, this circuit will look strictly RL. And at other frequencies, this circuit is strictly going to look like RC. So you have to know frequency if I don't give you X sub L and X sub C. And I didn't in this case, and in some cases, I'm not. So what I'm going to have you do in this problem is I'm going to have you find the total impedance looking into the circuit and the output voltage. And I'm going to define the output voltage here as the voltage across both of these elements. That's what I'm going to call V out. I want you to find the total impedance looking into that circuit and V out when the frequency of this source is 60 hertz and when the frequency of the source is 400 hertz. Two separate problems. Now, I want you to take a look at part A. Part A is I want you to find the total impedance and the output voltage when the frequency is 60 hertz. I want you to take your time. I want you to work through the problem. First thing you're going to calculate is total impedance. I calculated the total impedance to be 25 minus J, 45.51. It turned out that the capacitive reactance of this circuit was much greater than the inductive reactance, so that capacitive reactance completely eliminated the inductive reactance and there was some left over. Matter of fact, there was 45.51 ohms left over. So at 60 hertz, this circuit looking in looks like a RC circuit. That right there is going to be my impedance. Since I know the impedance of the circuit, I can take the phasor voltage and divide it by that impedance to get the total current of that circuit. The total current of that circuit is 0.96 at an angle of 91.22 degrees, and that's in amps. Now that I know the current in this circuit here, only one path, I can take that current times just this impedance here, which turns out to be reactive. And we know at that frequency what it is from here to here. We know it's strictly the 45.51. So what I did was I went ahead and I made the calculation that the output voltage is simply going to be equal to the total current times that reactance. In polar form, it's 45.51 at an angle minus 90 degrees. I end up with an output of 43.7 at an angle of 1.22 volts. So there's my output voltage, and there's my impedance at 60 hertz. At 400 hertz, I did the same thing. I made a calculation for total impedance at 400 hertz. That's my total impedance right here. I did it in rectangular form. Notice that the capacitive reactance completely eliminates, the inductive reactance completely eliminates the capacitive reactance up here, and I end up with inductive reactance left over. So that circuit at 400 hertz is 25 plus J, 42.31. There's my total impedance. I put it in polar form So I can divide it into the voltage to get my total current. There's my total current. Once I know my total current, I can find V out, which is equal to the total current times that impedance, which is purely inductive reactive. It's that plus J 42.31 is equal to 43.2 and an angle of 60.58 degrees. That's in volts. Now notice I could have found the output voltage another way in both cases here. And you might want to look at this and make the calculation. I can use the voltage divider rule. In both cases, I could have took, once I know the impedance, and I know the impedance from here to here, I could have taken the total voltage here times just this impedance divided by the sum of all impedances. And I'd have got the same answer for voltage. That would have eliminated this step in both cases. You get the same answer minus round off error. Now, before I take a look at this in terms of sinusoids, which is what I want to do, and I'm going to continue with this problem, I want to point something out here. Remember when we had these circuits, we had a step function, we ended up closing a switch that looked like this. We had a circuit that maybe, let's just use the capacitor. Here's a capacitor, here's a resistor, and we closed that switch at t equals 0. We had some voltage out here. And we said when we first closed that switch, that capacitor looks like a short circuit because all the charge is trying to run to that plate. And that charge builds up, and consequently so does the voltage exponentially. Well, what's the voltage look like at this point when you close that switch? It looks like a step. It looks like a step like that. It's a step function to 10 volts, from 0 volts to 10 volts when you throw the switch. There's a lot of high frequency in that step. A Fourier analysis of that step function right there, there's tremendous amount of high frequency sinusoidal waves that make that up at a very high frequency. So at a very, very high frequency, you know that capacitor looks like a short circuit. That goes directly to this formula right here. At a very, very high frequency right here, this approaches 0 as F gets very, very high. Capacitor reactance goes to 0. On the other side of that, what does it look like at DC? At DC, there's no frequency. The lowest frequency you have is 0, and that's DC, and that's exactly what you have in this case. That looks like an open circuit. Looks like infinity resistance. Well, let's take a look. It goes right to this formula again. As frequency goes to 0, you get a 0 in the denominator and takes this whole function to infinity. So both this function right here and this equation here and this equation here tie into the fact that when you first throw switches like this, inductors look like an open circuit and capacitors look like a short circuit. And then t equal infinity, the inductor looks like a short circuit and the capacitor looks like an open circuit. You go back and you look at it all in terms of these equations right here. You have to think about that. All right, let's get back to this problem here and let's finish it up now. I've calculated the current and I calculated the output voltage in both cases for frequency equals 60 Hertz and frequency equal 400 Hertz. We know at the lower frequency at 60 Hertz, this looks like a capacitive circuit, an RC circuit. But as the frequency goes up and up and up, we get at 400 Hertz, somewhere between 60 Hertz and 400 Hertz, we cross into a situation where this circuit looks inductive. We're not worried about where that point is right now. It's the point of resonance. But we're going to talk about that coming up in a week or so. It's at the resonant frequency. Now, what I did was, at 60 Hertz, I took a look at the waveforms. And I said, let me use the current waveform as a reference. Well, if we look at the current waveform as a reference, all we'd have to do is realize that the current goes through that resistor right there. Now stay with me, this is important. That current flows through that resistor, and through a pure resistor, we know the voltage is directly in phase with that. Just between this point and this point, that current has to be in phase with the voltage across that resistor, because from here to here, it's purely resistive. So if you'd monitor the voltage across there, what we're really doing is on a scale factor. We're monitoring the phase of the current. So what I'm doing here is I'm plotting that current waveform, and I'm labeling it at 0 degrees. I'm going to start referencing at 0 degrees. Now you look back here and say, well, we don't have 0 degrees there. We have about 90 degrees. So let's just subtract 90 from that. Let's subtract 90 to get that as a reference point. So that 0.96 is at 0 degrees. And that's what I plotted here, what we would see on the oscilloscope. Well, if I'm subtracting 90 here and I want to relate these two together, I better subtract 90 here. So do you see what that does? It makes this somewhere in the neighborhood of about minus 90 degrees, minus some of this round off air. Minus 90 degrees. If I subtract 90 up here, I have to subtract 90 down here to keep these in the same relationship. Well, when I did that, I plotted that output voltage right here, and I started at this point and I drew that in. You know that that's a minus 90 degrees. You know that the current is leading that voltage waveform right there by 90 degrees. Because you're over here and the waveforms come toward you in this direction. Remember I said anything to the right of this axis here is going to be represented as negative. Anything over here is positive. We talked about that. So you can see the current leads the voltage by 90 degrees at 60 hertz. Well, you would expect the current to lead the voltage by 90 degrees at 60 hertz in part A because it looks like a capacitive circuit and voltage can't change instantaneously across the capacitor, so the current has to lead the voltage, and that's what you would see on an oscilloscope if we built this in lab. You'd see this. Don't forget, this current is really the voltage across. We're just interested in the waveform, not the magnitude. This is really the voltage across the resistor, but it's the same phase as the current through the resistor. What about down here? At 60 hertz, what I did was I used the current as a reference again, and I drew it as a sine wave starting at 0 degrees right here. Well, the current was minus 29.42. So how do I get that to 0? I have to add approximately 30 degrees to that. So if I'm adding 30 degrees, I better add 30 degrees to this one to keep these in the same phase relationship. So I added 30, I get around 90 degrees, so I can plot V out too. It's a plus 90, so I plot my V out voltage here. This is what I'd see on the oscilloscope. Do you see that the voltage is leading the current by 90 degrees as these waves come in this direction? The voltage waveform is ahead of the current waveform, and it should be, because at 400 hertz, this circuit looks inductive, and current can't change instantaneously across or through an inductor. So the voltage is going to lead the current at 400 hertz by a pure 90 degrees. Because we're just looking at the output voltage between this point and this point, and it's either going to be purely capacitive like it was in part A, or it's going to be purely inductive like it was in part B. That's a nice way of analyzing this circuit. It shows you that the circuits can either be inductive or capacitive. It depends upon the frequency. If we could set up a frequency generator, and we could do this in lab, well, we could vary the frequency between 60 and 400 hertz, and you can do that with our frequency generators. You can set up a sweep, they call it. It starts at 60, and over maybe 10 seconds, it sweeps to 400, and then it sweeps back to 60, and it goes back and forth. What you would see is you would see this waveform initially at 60 hertz, and then as the frequency went up, you'd see that voltage waveform shift over to here. And as the frequency goes back down, you'd see this voltage waveform shift in this direction, finally back over to here. And you would just see this voltage waveform here shift like this as you sweep the frequency from 400 hertz up to 60 hertz. 400 hertz down there, back up to 60 hertz there. And that shows you that the phase relationship will change as the frequency changes, because the values of X sub C and X sub L change with frequency. It's a very nice way of looking at this example. And that concludes this amendment to video 8E.